I'm very pleased to welcome Professor Richard Barker from the University of Otago, who is a very well-known statistician in our community, but has also more recently moved into senior administration and is the Pro-Vice Chancellor in the Division of Sciences at the University of Otago. Richard's research interests include Bayesian inference and in particular hierarchical models. He's interested in developing theory and methods and applying statistics to fisheries and wildlife ecology, to sports science and exercise physiology and climate change. And he's made important contributions in all of those fields. He's particularly interested in mark recapture, or capture-recapture as it's sometimes called, and radio telemetry. And indeed, this morning, that's what he's going to be talking to us about, continuous time capture-recapture. Richard.
Thank you, Tao, for the invitation, and Alan for the introduction. It's an auspicious day. I just realised it's the 5th of November, and in New Zealand we still celebrate Guy Fawkes, which is when the Catholics tried to blow up the Houses of Parliament in 1604. So, you know, you wonder if there's some kind of parallel with what's going on in world politics at the moment. But anyway, from memory, the Australians don't celebrate Guy Fawkes. I actually spent some time growing up in Australia, finished primary school there and started high school. And I think from memory, it was Queen's birthday that is when fireworks exploded and whatnot. Anyway, thanks for the invitation. So why this particular problem? I thought I'd, you know, in the choice of problems that I had to talk about, the first thing was to try and speak on something that I could remember something about. I'm not doing so much research these days. I've been in my current role for 4 years, and although the university expects its senior leaders to maintain their research output, that is a challenge. But this problem I thought might be interesting to staff at ANU, because there is a connection with ANU in this work through Chris Hyder, if I've got the pronunciation of his surname correct, or Hayder. And as Alan mentioned, I have a long interest in capture-recapture. In fact, I can claim it's almost a lifelong interest, because I can remember being read a book when I was 6 years old about a tagged salmon that captured my fascination. And I think that's when my interest in this particular problem began. But the continuous time version of capture-recapture is a class of problems that has had relatively little work done on it. And I came into this by accident. I'll say a little bit more about how this piece of work came about, but it had the nice attribute of teaching me a lot about things that I had never really understood very well. Things like counting processes and notions of information and ancillarity. So I now know a bit more about those, but I'm certainly not an expert, and you'll have to excuse any statistical faux pas along the way. The other nice thing about this problem was that at the conclusion of the work that we had done on it, you know, I'd been able to tidy up a whole lot of loose ends in my own mind about capture-recapture and how the continuous and discrete time formulations interacted. So it was fun for all sorts of reasons. And I should say this is joint work with Matthew Schofield. Matthew was a PhD student of mine who we recruited at the University of Otago, and as all good PhD students should, is seriously outshining his supervisor in the work that he does. Normally, when you think of capture-recapture, it's described in terms of the discrete time formulation. And the basic idea is that you have a sequence of samples from the population. Each sample in the sequence is drawn without replacement. We have K such occasions, and between the occasions you put the animals back. So at each occasion you draw, you look to see who's marked and who's not, record that, and apply marks to any of the unmarked individuals, and then let them all go back into the population, and then leave them for a period, and then repeat and rinse, as they say. So that's the discrete time formulation. With the continuous time formulation, we now switch to sampling with replacement. Now, you could have just one sampling occasion where you visit the field site once and do the sampling with replacement. You could break it up into discrete visits where you repeat this on multiple occasions, but on each occasion you're sampling with replacement. You may keep track of the times at which you capture the individuals, or you may keep track of the sequence in which they appear, or you might just count up the number of distinct individuals that were caught during the visit. And it turns out that the loss of information in that sequence that I just described may or may not have implications. The earliest example that I've come across for this type of modelling is a paper by Craig in 1953, and it was subsequently followed up by John Darroch in 1958, who's another statistician with very strong Australian connections. I believe he's still in South Australia. Somebody might be able to tell me if he's still with us. I think he is, but I'm not actually sure. Niels Becker at La Trobe. Oh, I've just spotted a typo. I corrected it this morning because I had 2004. It was actually 1984, not 19,844. So Niels Becker published a paper in the Australian Journal of Statistics that was really the first serious proper theoretical description of this problem. And he followed it up in a paper with 1990 that was jointly published with Chris Hayder from ANU, another very distinguished statistician. Paul Yip in Hong Kong and Ann Chow in Taiwan published a bit on this in the mid-1990s. And then we saw some more work from Wen-Han Wang in Taiwan 2002, and Shi et al., who was a student in 2007. And that little list there pretty much covers most of the literature on this. And I can remember first encountering this probably in the early 1990s. And it was all about martingales and estimating equations. It was all terribly complicated. It wasn't until really Wang in 2002 and Shi's work that we started to get more familiar descriptions and maximum likelihood estimators. So part of the story here is that the continuous time work has been quite complicated in its descriptions. One of the interesting features is that it turns out that the estimating equations for abundance don't depend on the times of capture, so that's interesting. And the estimator for what we call the model M0. So M0 is the model where all the capture probabilities for the animals in the population are assumed to be the same at each of the capture occasions. So remember, we had in the discrete time formulation, we have a sequence of capture equations. Under M0, there's a single parameter P that governs the capture probability for all occasions. One of the interesting things about the continuous time models is that if you do have sessions, the estimator for M0 is the same as for MT. So there's something about the lack of dependence on time that's interesting here. And similarly for the models that we call M sub H, that's heterogeneity, where each individual has a different capture probability, but it's assumed the same at each of the capture occasions. And MTH, which is, we have time dependence and individual variation. And under the assumption that the individual variation is carried across time, for each individual, the estimators for MTH and M sub H are the same. So again, there's this idea that somehow things don't depend on time. Back to the comment I made a second ago about the relative paucity of work on this. She, et al. In their 2007 paper, commented that compared with the discrete time model, there's been relatively little published research for continuous time counterparts, which is the point that I was just making. And also that this is again a quote, the unavailability of the continuous time capture-recapture data models could be attributable to the non-existence of continuous time estimators. I think non-existence is probably a bit strong. More to the point, there have been estimators available, but they've been hellishly complicated for people to work with. As I said, I got into this quite by accident. I had a student, Janine Wright, back in 2009, who we put to work on what was really quite a fascinating problem. And this was capture-recapture models making use of DNA data. And the problem that we used as our example in the work that we published on this was for European badgers in the United Kingdom, where the lucky researchers sampled badger latrines. So badgers have a common latrine that they use, and they deposit fecal matter in there, and along with that, they shed DNA. And so the researchers were using this field sampled DNA as a basis for their capture-recapture model. So instead of having tags that have been applied, they used DNA microsatellites to individually identify the samples. And what made this problem worthy of a PhD was that there's a phenomenon called allelic dropout. So when they do the DNA reading, they take small amounts of DNA, and I think of it kind of like running it through the photocopier. They use a process called PCR to amplify the DNA till they've got enough to be able to read it in the laboratory. And allelic dropout is a phenomenon where, if you know your genetics, you've got two alleles at each point on the genome, or each locus, one from mum, one from dad. And allelic dropout occurs when only one of those alleles gets amplified by the PCR process. And so what that will mean is that if you've got a heterozygote at that particular locus, so you've got big A, little a, or something like that, only one of those gets picked up and amplified. And so you end up with an excess of homozygosity. And of course, using these as tag reads, you're going to make a mistake in the reading of the tag. You could have two identical bits of DNA, one subject to allelic dropout, one not, where you would end up thinking that you've got two different individuals. So that's what made it interesting. And so the work that Janine Wright did on this was to look at incorporating a model for the DNA corruption into a capture-recapture model to try and adjust for this error that comes about from DNA corruption. The field sample that we used for this was a very, very simple one. And if you remember the story, they were reaching into the latrines and pulling out badger droppings. They were reading the tag number, and there was a rinse and repeat. And we thought that we could treat that as sampling with replacement, because there's a lot of fecal matter in these latrines. So effectively, we weren't really depleting it each time you took the sample out. And the model that we used assumed that every badger was equally likely to be caught. So as a metaphor for sampling, if you like, you can think of it as having a jar of jelly beans where each jelly bean has a different color, and you're sampling with replacement. So you're, and if you draw T such samples, so that's the notation that I've got up here, the data that you see is a sequence, which I'm going to call Y, of identities. You might see yellow jelly bean, then a blue jelly bean, and then a yellow, then a red, and so forth. And you can see how that gives you information about the population size, because if you're getting a steady accumulation of colours, you'd be left thinking that the population is quite large. If you only got a few colours and got lots of repeats of them, you'd be inclined to think the population was small, and close to what I've called little n there, which is the number of distinct individuals that appear in the sample. So that was the field sampling model that Janine used, and it's perhaps obvious, I don't know, that the distribution of that sequence given the number of animals in there actually just boils down to a permutation term, and then 1 over n is the probability that any individual gets drawn in a particular sample, and then that's raised to the power of t. So that's the simple model. And it's called CapWire because it was published by a group working in Idaho in 2005. They produced a little piece of software called CapWire, and that was essentially the likelihood that they used. They didn't actually have the capture sequences. What they had was just the number of times that each individual had appeared in the samples. So, and the probability distribution, you'll have another term in there for describing that, but that only depends on the capture frequencies. It doesn't have the abundance in it, so the likelihoods are going to be proportional. So that was how we first began to think about this particular model. It was just a model that we used in this broader problem of how to account for DNA corruption in these capture-recapture type models. Then fast forward to a conference that I went to in Kent. It was part of the ISEC series. I think it might have been about 2012. And I was having lunch with Matt Schofield, as you do, and we got talking about this, and he challenged me on why we were conditioning on that statistic, capital T. So capital T is the total number of samples that you drew from the latrine or from the urn. And if you had predetermined that, said, well, I'm going to draw 100 samples, then you're perfectly justified in conditioning on capital T. But of course, in reality, that capital T will itself be a random variable, and it's likely to depend on the abundance capital N. And the best example that I can think of to illustrate that is a piece of work that was published by Mondol et al. In 2009, where they did same sort of sampling approach was followed, and they were interested in tiger abundance. And so they were sampling tiger scat, as it's called, tiger poop. And I don't know about you, but if I was the field technician out there, if I was finding a lot of tiger poop in the area that I'd been assigned, I would be very nervous relative to if I was hardly ever finding it, because a lot of poop would suggest that there might be a lot of tigers out there. So that the idea then is that this statistic T will itself depend on the abundance. And so this is what got me thinking about it. And my response to Matt when he challenged me on it was, I said, well, I suspect it's going to be like an ancillary statistic, and it's something that we can ignore. It won't really tell us anything about abundance. But of course, lurking in the back of my mind was this notation that capital T probably is going to depend on abundance. And since we thought of ourselves as Bayesians, perhaps we were missing something from the model that was important, or failing that, we needed to come up with a justification for why ignoring that information was a reasonable thing to do. So that got us thinking about sampling in continuous time or space, because we thought that would be a natural representation of the problem that we're working with. In the context of the badger latrines, the field biologist is going along, drawing a sample out. That's going to take time to process, and then they reach in again and take out another one. So you can imagine that there were times associated with each of the draws. So the basic formulation that we thought would be appropriate would be to think of this as a counting process. And so in this notation here, capital CI of little t is the number of times that individual I is caught in an interval from 0 to little t. And that's going to be bound by 0 and tau, which defines our sampling session. So we're going to say that our sampling session runs from time 0 to time tau, and then these little t's indicate the time at which you drew each of the sample, and at any point in time you can count up how many times an individual has appeared. So that's the idea of the counting process. People who know far more about stochastic processes than I do will tell you that if a counting process is orderly and you have independent increments, then you will have a Poisson process. So, I mean, they strike me as relatively mild conditions. Perhaps the independence one is not so mild, but relatively mild. Now, the way we thought about it was that each individual is going to be subject to one of these processes. And so you've got a whole series of these counting processes running through the experiment. And if they're independent amongst the individuals, then you could describe this using what's called a superposed Poisson process. And so that was the foundation of the work that we did. So to provide a little bit more notation, I'm going to talk about little ci. So sorry about any potential confusion with capital CI, but little ci is going to be the number of times that individual I featured in the samples that were drawn in this session from 0 to tau. And that's going to be indexed from 1 through to n, which describes the size of our population. Tij will be the sample time of the jth appearance of individual I in the sample. And then capital T, which I introduced earlier, the total number of samples that are drawn, that's going to be equal to the sum of the little CIs across the population through the experiment. So the idea of the model is to model the collection of Tijs for each I, sorry, the collection as a realization, no, that was right. The collection for each I is a realization of a Poisson process. And then because we assume that they're independent, we then get our superposed process. But for each individual, we would have an intensity function lambda I of T. Now these sample times, even though they're featured in the model, may or may not be recorded by the person doing the fieldwork. It turns out that it doesn't really matter if they do or not, but we do have to think about these times, to just think about the implications of the information that we've ignored. So graphically, here's a representation of what we think might be going on. I'm God here, so I can assign a number to each of the individuals in my population. So I'm going to have individual 1, 2, 3, and 4. That's only known to me. So that's, you know, like the unknown soldier, known only unto God. So we've got labels on each individual, which are these indices, in this case 1 to 4. And if you look at individual 1, through the experiment, they got captured at this time here, and then this time here, about a little over a third of the way through the session, and then another capture toward the end. So individual 1 got caught 3 times, and we may or may not have a record of that time. Individual 2 got caught just once, coloured in red here, but over a third of the way through the experiment. Individual 3 got caught twice right at the start of the sampling session, and then 3 more times after the halfway point, and then my individual 4 never got sampled at all. Now, from the perspective of the person doing the field work, they don't know about these indices that only God knows about. What they see is early on they caught 2 individuals, and we'll call them A because they were the first individuals that we encountered early on in the experiment. A little later on, we saw individual B. Now, A here corresponds to our individual 3. B corresponds to our individual 1. Then we saw about a third of the way along another individual, so we're going to call that C, give it a new label. And that was actually individual 2. Then we saw B again. Remember, that was individual 1. and then another couple of appearances from A, which was our original our individual 3, and then a final appearance from B, then an appearance from A to round out the sampling session. So the data that we're going to have to work with as statisticians is this sequence A, B, C, B, A, B, A, the sequence of identities. And as I said, we may or may not have the times recorded for the appearance of those individuals. But this thing down here is the observation of the superposed Poisson process that's made up of these 4 components here. So that's the sampling setup and the basic model for that we should use to think about how we go about making inference about the parameters of interest. So if we use J to correspond to the latent indices, the ones only known to God, they go from 1 to n, and then I'll use this script C to denote the indices of the individuals that appear in any of the T samples. Then the model for the collection of times, if we observed them, conditional on the intensities lambda and the abundance n, with a little bit of rearranging of the standard result for a Poisson process, we can write that as a product of Poisson terms for the number of times that individual J appeared in the samples, and then a product over the set of indices here for that's basically modeled the times of capture conditional on the number of times each individual got caught. And I've expressed this in terms of a parameter nu here, which is the integral over the sampling session of the lambda I parameter for individual I. So that's basically the encounter rate for individual I right through the experiment. So that's the basis of the likelihood function. Now remember, if we go back to this previous slide, what I've just described is the product over these 4 lines here in terms of the times for each individual. But what we actually observe are the encounter times for the individuals that I've indexed down here using the color sequence. So that's really what I'm trying to say by this line here, that the indexing is arbitrary. So if we adopt indexing by the order of appearance in the experiment, then we can write down the model for the observed times conditional on our vector of functions, lambda, and the abundance as the product across the individual of the Poisson terms with this product across the individuals that we caught of the times conditional on the number of times they got caught. And then we add in this permutation term to account for the fact that there's all a different number of ways in which we can get the sequence A, B, C, etc. from the true indices that are unknown to us. So that's an important term for making inference about the abundance, a critical term. So I'll call this F1 of C, given the parameters N and U, and then F2 of the observed sampling times conditional on the capture times in lambda. And when you look at that, you may make the observation that you can write this term over here, lambda I of T divided by the set here. You can actually rewrite this in terms of a function phi I of T, where phi I is lambda I of T divided by that integral nu I. And so if you stare at that a little bit, you could convince yourself that perhaps what's really going on is that the times, what they do is they tell us about the shape, if you like, of the individual intensity function, and that they don't actually provide any extra information about the integral nu once we've used up the information they contain to describe the shape of the intensity function. So that suggests that we can probably safely ignore the capture times if we want to make inference about the abundance n, because n doesn't appear over here. we might be bothered by the fact that the new appears in both pieces here, but perhaps we could convince ourselves that the term T given C is uninformative about N, and perhaps it doesn't tell us anything about the news once we've used it to describe the intensities. But of course, in the introduction, Alan pointed out that I characterize myself as a Bayesian statistician. And when you're a Bayesian statistician, you get rather nervous about dropping terms out of a model arbitrarily. So this is something that causes a little bit of concern, but maybe you could argue that these T's are ancillary in some sense because they're uninformative about the terms that we're interested in. So that would be ancillarity with respect to the abundance N at least, and perhaps nu. So that's an idea, but as an idea, it needs to be thought through. So I'll take a little brief excursion now on by thinking about this problem in terms of three very simple experiments to help focus the mind on ancillarity. It might sound like a teaching device, but the truth here is that I can only understand these things if I can distill them down to simple little examples. So that's really why I did this. But the first experiment is we're going to carry out a pair of binomial experiments. In the first experiment, we're going to draw a random variable x from a binomial distribution that has a parameter nu and phi. And this nu and phi have got nothing to do with the nu and phi's that I've just been describing in my capture-recapture model. In this case, nu is the index for the binomial distribution for x, and phi is the probability. Now, my second experiment, we're going to draw a random variable y. We're going to condition on x. So x is going to be the index in our second experiment. And the capture probability or sampling probability for y is going to be governed by parameter pi. So if you focus yourself on inference about pi, then x is the very definition of an ancillary statistic that you would find in a textbook. Yes, it's a random variable, but the distribution for x is not governed by pi in any way. And so we're justified in conditioning on x for inference about pi, which is going to depend entirely on the observed value of y relative to the x that we drew. So in this case, nu, pi, and phi are all unknown. And just for example, we might have in the first experiment observed x equals 20 and y equals 15. The only inference that we can make out of this is that we would hazard a guess that pi is approximately 15 out of 20 or 3 out of 4. And so we could come up with a judicious guess for pi. We can't say anything about nu or phi based on the information that we have. Just a question. Do you routinely interrupt for questions, or do you just let the poor old speaker drone on and then take them at the end?
We usually take them at the end.
Okay. Well, there is an invitation there to shout out if you wish. So that's experiment one. Now let's make it a little bit more interesting, and we'll go to experiment two. What we do with experiment two is we'll say that the probability for the binomial distribution for x is the same as the probability, the binomial distribution for y. And might take some convincing, but this for me is sort of the simplest reduction that I've ever been able to come up with for what really goes on with the capture-recapture experiment. The y's in a capture-recapture experiment are used to gain inference about some sort of overall capture probability, which is then fed into a term that gives you inference about the abundance, which is the equivalent of nu here. And you get these statistics appearing in both parts of the model. So in this second experiment, the first thing you might think about is the fact that if you write out the joint distribution of x and y, you're going to have the product of these two binomial terms. You're going to have a nu choose x, and then a pi to the x, 1 minus pi to the nu minus x. And then you're going to have a second term, x choose y, with a pi to the y and a 1 minus pi to the x minus y. So in both terms, you're going to have a pi to the x. And you're going to have a pi. You've got a pi to the x in the first term and a pi to the y in the second term. So you're going to be able to rewrite that as pi to the x plus y. So clearly the statistic x is not an ancillary statistic because it's part of the sufficient statistic set. So you could think of it as a sufficient statistic for pi. So it's clearly not ancillary. So the term x given u, which is the first one, obviously contains some information about pi, and there's some sort of residual information that's left over even after you've made inference about nu. So there's going to be some information from that first term that's going to need to carry through along with the information in the second term if you're going to make use of all the information in the experiment. However, thinking again about the product of these two binomials in that second line, you might reason, well, pretty much all the information that's going to be worthwhile about pi is going to come from that second term. So I could use that as a partial likelihood for pi. And as before, I would guess that pi is about 0.75. And then if I pass that across to this first binomial, where I modeled x as a binomial nu and pi, then we would guess that our parameter nu would be roughly 20 divided by our pi hat, which would give us 400 over 15 or 80 out of 3. Now those are not the maximum likelihood estimates for this particular problem, but you would think they're pretty good ones. And formally we would regard this as some sort of two-stage process. And this is something that you see carried out in capture-recapture experiments where people will use two-stage estimation to make inference. Now, just an interesting observation that I'll come back to in a minute is with this model here, model 2, and again, we're focusing our inference on the parameter pi here. If we put a scale prior on the parameter nu and then integrate that out, what we'll be left with is a constant times this binomial term here. So that would give us a Bayesian justification for using the partial likelihood, because by judicious choice of prior, we can reduce all of the information about pi to the contribution from this term here. So just hold that thought in your mind, that I can get an integrated likelihood that corresponds to that partial likelihood, which would give me some justification for using that partial likelihood. Okay, now let's think about a third experiment. The third experiment, it's exactly the same as the second one, but instead of drawing our x from a binomial distribution with parameters nu and pi and expectation nu pi, we'll draw it from a Poisson distribution that has the expectation nu pi, and then we have the same thing for our y. And in this case, you can convince yourself with a little bit of effort or not much effort that in fact the intuitive estimators, or using the partial likelihood to get at pi, and that gives us pi hat of y divided by x, passing it across into the first term where we model x in terms of the product, corresponds exactly to the maximum likelihood estimators. So doing the two-stage process approach here for model 3 gives us the MLEs. And what's going on here is that because pi appears in the product with nu here, we could reparameterize this third model as x is Poisson, let's say phi, which equals nu pi, and y is binomial x and phi. And then we now have a similar situation to what we had with our first model, where we've got a phi here and we've got a pi over here. They're distinct parameters, and it's just like the ancillarity example. But because pi actually is in here, it's not strictly X is not an ancillary statistic for the parameter pi here, but it turns out that it's given the name S ancillarity, and this goes back to work that was done by, excuse my pronunciation, Barndorf, Nielsen, and Blaesild in 1975, where they described this notion of a statistic that's S ancillary. And in this context, as far as the inference about pi is going, X is acting as an ancillary statistic because of this property that we could make this substitution for our new parameter phi in here that equals nu times pi, and it then appears to be distinct from pi. So this is this notion of S ancillarity. Now, a paper that came out in 1995, I think was the first time this notion appeared, by Severini, he extended the idea to pick up this case that I talked about for model 2, whereby an appropriate choice of prior on nu, you end up with effectively the same result. And he called that Bayes ancillarity. So he introduced this idea of Bayes ancillarity. And so with a judicious choice of prior, we can reduce this to the partial likelihood for inference about pi, and in effect, we've used up the information that X contains about pi in this second term through our inference about nu, and it's obviously moderated by the prior that you choose. Now, S ancillarity implies Bayes ancillarity, but it doesn't go in the reverse direction. So if a statistic is X is S ancillary, then it's also Bayes ancillary. So there'll be a prior that you can use to justify the use of the partial likelihood, but it doesn't apply in the reverse direction. So those are the concepts of S ancillarity and Bayes ancillarity. So now let's go back to our example that we're working on. And this is a slide I put up with the observed data likelihood here. And now what you can argue is that because we can write this term over here, lambda I t's, this product over here, as a product of lambda I over t divided by nu I. So we've got our nu I appearing in the product with this term here, that in fact the times of capture are S ancillary for our parameter nu in the presence of this function lambda. And so that would give us justification for ignoring the second term over here that I've called F2 and making inference about the news and also about the abundance, because all the information that we have is carried through the number of times that the individuals were caught, which we can extract from the information about the times of capture. So it all appears in this first term, and that the second term, which models the times of capture conditional on those number of times that individuals were caught, effectively we could ignore this term, and so they're acting as ancillary statistics like in our model 3 example. So that justifies ignoring that right-hand term. Now, if we carry on and, we can either ignore it, or if we haven't observed them, we can integrate them from the model, which I've done. In the second line here, and this is one of these, you'll just have to believe me that it works out like this. I had to remind myself how I did this yesterday when I was preparing for the seminar. It turns out that if you go back to this partial likelihood here, reason that you haven't observed the t's, and so you integrate them from the model, that you end up with this expression here. The alternative is that you just ignore this term and you end up with a slightly different expression up to constants. So because we've got S ancillarity, we can argue that we're justified in using just the first term in that observed data likelihood, which models the observed sequence of y's conditional on nu and n in this way here. Just looking at my notes. We now introduce a new constraint. So now we get back to the model that we're interested in, model MT and model M0. We make the constraint that the intensity functions for each individuals are all the same. So instead of having a lambda I of t, we now have a lambda of t, and hence our nu sub i's all correspond to a single parameter nu for each of the i's. If we want our model M0, where the capture probability is constant over time, the analog would be that the lambda t function equals lambda for all t, then we're also led to the same likelihood function where we have the nu I is equal to nu for all I. And our observed data likelihood can now be written in this form here, which has got two terms, F1 and F2. And the two things that you should notice here is that this term F2 is exactly the cap-y likelihood, if I zoom back, that I described when I talked about the Wright FL work. And the second observation is that the new n, capital N and nu parameter appear as a product here. And so we could reparameterize that with we could call it phi, n nu, we could replace that as a phi, and we've got another one of these examples akin to our model 3. And so the statistic T, which is the total number of individuals that were, the total number of samples that were drawn, is S ancillary for n in the presence of this new parameter. And so I was able to report back to Matthew that there was in fact a ancillarity explanation for why we could ignore this parameter capital T, even though it is going to be related to our abundance parameter. Because it's related in this particular way, we're justified in ignoring this first term and using our partial likelihood, which was the cap-y likelihood, for inference. So as you can imagine, I was quite pleased to finally derive that result. Let's briefly talk about the heterogeneity models. For the heterogeneity models, one thing that we could do is model the nu I parameters as a parameter nu I equals gamma I, which is I think it's a frailty term for each individual, times a constant intensity function. So this is a particular type of heterogeneity. And if we model it that way and model the nu i's as exchangeable gamma random variables and integrate them out of the model, we end up with this lovely looking expression here. But what you'll notice is that we've got two terms here. The first term we can write as a negative binomial probability mass function for the statistic T, and it depends on two distinct parameters. The first one is the product of our n and alpha parameter from the gamma model, and the second one is the beta parameter from the gamma model. Now, because we've got two distinct parameters here, we've got a beta and we've got an n alpha, we're not going to have S ancillarity. To get that, we'd need all three of them to be in a product. But we do have Bayes ancillarity, because if we choose the right prior, and the prior that I've got here is that our parameter lambda, so it's a reparameterization, lambda equals 1 over 1 plus beta, that if we make the prior on that proportional to 1 over lambda, 1 over 1 minus lambda, so it's an improper beta prior, isn't it? Then we get, when we integrate the beta out of the model, we end up with, I think it's 1 over t times all of this stuff in the second term here. And so we can use the second term as a partial likelihood. So once we've made inference about beta using the t's up here, under that choice of prior, the t's don't contribute any more information for inference about n and alpha, other than appearing as effectively an ancillary statistic. So we don't have S ancillarity under model H in this particular version of it, but we do have Bayes ancillarity. So with judicious choice of prior, we can justify using this partial likelihood here. The final set of models that I haven't discussed here, but if you're familiar with Capture-Recapture, you'll be familiar with the so-called behaviour models. And these arise when the behaviour of the animal is changed by the act of capture. So people will talk about trap-happy animals. So classic example is where peanut butter is used to bait traps for little rodents, and the little rodents discover that if they can put up with being held in the trap for a period of time, they can get a lovely free meal of peanut butter, and so they learn to go to the traps more often. So it's trap-happy behaviour. More commonly, you get trap shyness, where the animals don't like being caught, and so once they've been caught, that reduces their subsequent probability of being captured. Now, if you think about this, this is going to be a problem with the continuous time models if you don't have the times of capture, because the time of capture is going to convey information about this behavioural aspect of the model. And for example, an animal that only gets caught, 1 microsecond before time tau is going to behave quite differently than if it was caught just after time 0. It's going to have a different intensity function through the experiment. So the time of initial capture is going to be informative in this model. However, and I'm not quite sure how I did it, but I remember sitting down and staring at this thing, and I was able to cook up an urn sampling model, a bit like our jelly beans model, for model MBH, where the heterogeneity was modelled in the way I described for model MH, but with a behavioural effect. I was able to cook up a partial likelihood, but for that partial likelihood, the statistic T wasn't ancillary by any definition. So I know using that likelihood that there's some loss of information by conditioning on T, but by resorting to simulations, I was able to convince myself, at least in the examples that I looked at, it wasn't serious. So final slide, but one, pardon me. The implications of this work, well, first of all, the observations by Wong and Shi et al. About the fact that somehow time wasn't important in these models. Remember, the observation was that M0 and MT coincided, the maximum likelihood estimators coincided, and similarly for MT sub H and M sub H. Well, we can explain that in terms of these partial ancillarity results, that the times can be thought of as some sort of ancillary statistic. In the heterogeneity case, it requires a judicious choice of prior. A second observation is that we can model these continuous time models in terms of elementary probability distributions. I was using Poisson distributions and things such as that. And these are provide intuitive alternatives to the martingale and estimating equation approaches, which have dominated the literature on this particular problem, and that I suspect have made it quite daunting for people to implement. You can generalize this to space or space-time. If you go back to our likelihood here, that the times here might actually be, the T's you could replace those with spatial information, or both space and time. It won't really matter. The same theory will apply, and we can use that for inference about our parameter n. What I do think might happen is that if we want to also incorporate some notion of an area that the animals are being sampled from, and the reason people do that is so that they can rescale the abundance as a density, then my conjecture, if you like, is that there's going to be model sensitivity if you want to make inference about area, because that's going to come in through this term F2, and that you will have sensitivity to the density and abundance estimates depending on what you assume over here for F2. And that's just kind of a look ahead to thinking that this should perhaps be thought about in the context of the so-called spatially explicit capture-recapture models that have become enormously popular. So that brings me to the end of my formal part of the seminar. I've got some references here that people might like to look up if they are interested in this. And at this point, I should say I'm happy to take questions.
Thank you very much, Richard. I'm found that absolutely fascinating. Do we have any questions for Richard?
I have a question.
Thanks, Robert.
So Richard, that was mind blowing. So thank you for that. So partway through, when you had some of those very simple examples to show the ideas about ancillarity, you had one where where you said this is like the MLE. This is not quite the MLE, but it's about Wright.
Yep, that was model 2.
Model 2. If you use Stirling's rule to approximate the factorial, I think it actually is the MLE subject to using Stirling's rule. And I wondered if you thought about using Stirling's rule to try to maybe make a few of these likelihoods a bit more tractable.
I don't agree. I think using the approximation I don't think makes a difference. But when I say I don't agree, I don't unequivocally disagree. So I'd have to double check, but I'm not convinced that you're right.
I've just tried to do it for example too, and I reckon it is, but I could easily have made a mistake. But
right, well then I'll just say, well, you shouldn't be using Stirling's rule. You should be doing it properly.
Sure.
That would be fascinating if it's true, actually.
Right.
As a comment, Robert has had some success with doing that in other problems. So
right.
I'm not surprised he tried that during your talk.
I'm a bit sleep deprived from the US election, so I may have stuffed up my algebra. So
can I now dial up my degree of unequivocality, if that's the right term?
Thanks.
I mean, what's nice about that is that what this shows is that you can justify the partial likelihood as corresponding to a very specific prior. And that's the notion of Bayes ancillarity. And if what you're saying is true, then the use of Stirling's rule corresponds to a certain kind of prior information. So that would be fascinating.
Yeah, okay. Yeah, I don't know much about the Bayes ancillarity, so I'm not sure what I have to think about that.
Richard, I have a question about your implementation. I mean, do you actually just use these partial likelihoods, or do you begin with the bigger problem, think about a prior for the particular animal you're sampling, and then if you happen to reduce to the partial likelihood, use that, or otherwise just use the full model with whatever prior you think is most reasonable?
Yeah, good question. We haven't really done a lot of implementation. I mean, what happened is we implemented the Badger model, and then we used that as an example to illustrate all of this in the follow-up paper that all of this work's described in. And I'd have to go delving back. I think from memory that we used, for the Bayesian inference, we used Gibbs samplers. And so we never had the times of capture. And so we justified integrating those out of the model, which is convenient. And then implemented the rest of it. And from memory, for the model MT case, SL ancillarity corresponds to using a vague gamma prior on one of the critical parameters, perhaps new. And so we would have implemented it under that assumption.
Okay. And obviously, Huang and Ji didn't make use of these same justifications for going for that partial likelihood. So, do you know what they did? Would you like to comment on it?
Yeah, my memory's a bit hazy. They definitely didn't, because I gave this exact same seminar up to the errors that I corrected the last 2 days, and in Taiwan at Wen Hen's invitation. And yeah, he was really interested in it because it had justified some intuitive
Right.
work they had done.
Okay, no, that's great. Thank you. Are there any other questions for Richard? I think you've given us too much to think about, Richard, which
Apologies for that.
no, that's a great success and exactly what we want. So what we do now is ask you